Hi everyone, today I'll be covering conservation of energy. Just to give a little background information before we start the problem. Conservation of energy is simply defined as the initial total energy being equal to the final total energy, shown here. Since energy cannot be created or destroyed, this makes it easy for us to solve complex problems by converting energies in and out of their different forms. Here we show that the change in energy is the final minus the initial, which is 0 because of what's shown here. An example of the different forms could be translational kinetic energy, such as movement, gravitational potential energy, such as height, spring potential energy, which is found in the compression of a spring, etc. Those are just a few examples. When diving into a problem in which conservation of energy is going to be utilized, one of the most important parts is defining what's in your system, and this is because we want to be able to count up all the energy at different times and determine how the energy moves between the system and the surroundings. Because objects within a system cannot do work on other things within the system, this is important because when an object does work, it changes the energy of either itself or the other object, which is typically seen as a loss of heat through frictional events, or an increase or gain of thermal energy through something like deformation. So when defining our system, we want to be sure to include everything that you don't want to affect the conservation of energy. Doing so will allow us to have a relatively simple and easy calculation and not to worry about the nitty-gritty of work and energy being done. Now to get into a problem which uses conservation of energy, I've written this problem. Rosie and Jade are in a heated game of basketball at their local court. Rosie prances around the court, taunting Jade as she dribbles the ball to the three-point line, and then shoots the ball buckets. Jade, in utter disappointment, plans to get the rebound before Rosie has a chance to shoot again. Luckily, she learned about conservation of energy and might be able to predict where the ball will be. The basketball is 500 grams, so we're going to write in here 500 grams equals the mass. And Rosie shot the ball with an initial velocity of 5 meters per second. So we'll write here that she shoots it with 5 meters per second. We'll say that's VI, velocity initial. And the ball reached a max height of 5 meters. So this is her max height right here. So we'll say 5 meters is equal to height 1, let's just say. After shooting the ball through the hoop, it bounces back up towards Rosie with a final velocity of 7 meters per second. So we'll say here 7 meters per second is the final velocity, VF. What is the height of the ball at this point in time? So that would obviously be this height right here, which we can name as height 2. And that's what we want to find. So that's what we'll go on in the solution to find. So we know a few things about this problem before we can start calculating. We know the initial velocity, so I'll write here initial velocity is 5 meters per second, and we'll calculate that as VI. And then we also have our max initial height. Max initial height of 5 meters. This is all things we've already put in our drawing, which we'll say is height 1. We also have the mass of the ball as 500 grams. And we'll say that is just M. Final velocity we have as well given to us, and that would be 7 meters per second, and we'll say that's VF. And we also have the height after bounce with the ground. After bounce, we'll say is H2, and that's what we'll be solving for. We need to make a few assumptions before getting into the calculations. So we're going to assume, one, that there's no air resistance. So we'll put that down. We also want to assume that there's no frictional force present. Frictional force. And this is for when the ball goes through the hoop. Another assumption that we want to make is that there's no energy lost, and that will go into the conservation of energy. No energy lost here. And that means it's an elastic collision. We are assuming that that's an elastic collision. We can also assume, because of that, that it's instantaneous. And we are also going to assume the system, which is very important, and we want that to be the basketball, the hoop, the earth, and the court floor. Okay, so now I'm just going to explain a couple things before we go into the calculations. This appears to be an elastic collision, like we said, so we can solve it using conservation of energy. In the beginning, the ball has a given height, therefore we can calculate its potential energy, and it also has a given velocity, so we can calculate kinetic from that. Knowing this, we can calculate the initial total energy. Now at the end, after the bounce has already happened, the ball is moving with a given velocity, so we know it's kinetic. And it has an unknown height, which correlates to the potential energy. We know the initial total energy, like I said before, and because this is an elastic collision, the final total energy should be equal to the initial total energy. So we can now set up the two equations, and we can solve for the missing final height being h2. So we'll have 1/2 mv squared plus mgh equals 1/2 mv squared plus mgh. So this is going to be our mass of the ball. This is the initial velocity. I can put an initial there. Mass of the ball, gravity, height 1, let's say. 1/2 mass of the ball, velocity final here. And then we have mass of the ball, gravity, and the height 2, which we want to solve for. So then I can plug in my values, 500 being the mass of the ball, the initial velocity being 5 squared plus, again, the mass of the ball, gravity 9.81, height 1 is 5 meters, and that is equal to 1/2 mass of the ball, 7 is our final velocity squared, plus 500, again, the mass, gravity 9.81, and then multiply that by the h2, which we want to solve for. Doing all the math of that, we get h2 is equal to 3.77 meters because it's in height. So the ball will reach 3.77 meters after the bounce.